Hi everybody, welcome to another video in linear algebra section 4.1 vector space and subspace. A vector space is a non-empty set of objects called vectors. Now this extends into not just vectors, it could be anything, a set of objects on which are defined two operations. So there will be two operations in that. Of course, the first one is addition and the other one is multiplication by scalar. So that is standard addition and multiplication for a vector, subject to 10 axioms or rules listed below. Now, this is probably the first type of definition of something in this form. We'll see a lot in advanced mathematics. We define something that satisfies different rules. Like in this case, this have 10 different axioms. And so let's just go over them quickly. So first, the sum of u and v denote u and v is in v. So first, we assume that u, v, and w are vectors in v. By the way, by vectors, we do not mean a vector in traditional sense. A vector here could be an object or could be anything. Right. So u and v are vectors in vector space V. Then u and v, the sum of u and v are in v. So I put this one. Next, the scalar of u by c denote c times vector u is also in v. These properties I put together is called the closure properties, closure axioms, meaning that the combination of some objects will be some object in the set is also in the set. So u and v are in v, vector space v, then u plus v is also in v. That is closure. U is in v, multiply a number to it is also in v. And after the closure properties, we have this set of 4 axioms, and the set of these 4 axioms. These 4 axioms related to the addition, so all of them are the addition. So this exists a zero vector and exists the inverse. So this is from addition, and this for scalar multiplication. Now, so any non-empty set that have all 10 of these axioms is called a vector space. So it doesn't have to be a space of vectors. It could be anything that you see here. When we have these 10 axioms, we can prove that we have these properties. So the definition only have 10 of this, and then these are properties that can derive from these 10 axioms. Right, here's some example of vector space. As you see, it's not just a vector. The space Rn where n greater than or equal to 1 are the example of vector space. Definitely they are vectors. Even when we say Rn, it's not necessarily the vectors. It could be point or vectors, something that has n components. Right, so that is example of vector space. P sub n, a polynomial of degree at most n, is also a vector space. So polynomial, the set of polynomials degree at most n is also a vector space. So the vector space does not always, it's not always a vector. It could be a polynomial in this case. Yeah. And here's just another traditional vector if defined by the geometry sense. Right. There's more to that, but bottom line is the vector is a definition of vector space. The definition of vector space is not as simple as just a few sentences. It have to have all 10 axioms. Right. Now, subspace. A subspace of a vector space V is H of V that have 3 properties. So, subspace only have 3 properties. The first one, the zero vector of V is in H, and then it is closed under addition, and it is closed under multiplication by scalar. So remember I mentioned the closure axiom earlier. The subspace have to have those two along with the zero vector is in V. Right. Now, if you get to very advanced mathematics, then you might have to prove something that is a vector space. By proving something the vector space, we have to show that it satisfies all 10 of these axioms. That was too much for a course like linear algebra. However, in linear algebra, you will be asked to prove that something is a subspace, because for a subspace, we only need to verify 3 things. A zero vector belongs to the subset of V, is closed under addition and closed under scalar multiplication. Alright, a little note here. A subspace by itself is a vector space. So what is the difference between the vector space and the subspace? Well, the name say it. Oh, a subspace is a subset of the vector space. Because it is a subset of the vector space, the addition and the multiplication inherited from the vector space. So that's why in the subspace we do not need to prove this 4 and this 4, because those properties, those axioms inherited from a vector space. So the subspace will have those 8 properties already. We just need to show that a subspace by itself is closed, meaning that if you take 2 of them combined together, it's still inside that subspace. Of course, zeros have to be in that subspace as well. Right, so 3 things. Here's some example. The set consisting of only 0 vector is a subspace. In the subspace V, it's a subspace of V called the 0 subspace. It's not just a set of 0. Now we're going to check 3 things. The first one is the 0 vector is 0 vector in, I use that, it means in, or is an element of. So first is 0 belong to this set. Well, this is obviously yes. And then next, if you take an element of the set, add to an element in the set, do we still have an element in the set? And the answer is yes, that is still in the set. And then the third one, we take a real number multiplied by an element on this set. It's only 0 in this case. That also 0, and because 0 is in the set. So it is a subspace because it satisfies all 3 of these properties. Right? We will prove this in more example later. Right? Let P be a polynomial, own polynomial of real coefficient, and we define with operation like regular addition and scalar multiplication. P is a subspace of all real values function defined on R. And P sub n, the polynomial of degree at most n, is a subspace of P. Right, next. Is R2 a subspace of R3? The answer is no. R2 will be the set of the 2-dimensional vectors, or we can just say we have x and y. Could be anything, where R3 is x, y, and z, 3 components. So it cannot be a subspace of the other. So the first part is no. The next part is can we give some example of subspace of subspace of R3. Now, here's some example of subspace of R3. I could write this is the x-axis, only have the x values y and z equal to 0. This, of course, is a point in R3, right? I'm not going to say that, but I should say we have a subspace in R3. Subspace in R3. Also with the x-axis, or we could say something like this. This is the xz plane, y equal to 0. It's also subspace in R3. So these are some example, but they have to be 3 components. It cannot be that. It cannot be x, y belong to the space x, y, z. It is not. I said we will have more example later, so we have more idea of what a subspace means. Right, subspace spanned by a set. The term linear combination refers to any sum of scalar multiple vectors, and span of v1 to vp denote the set of all vectors that can be written as a linear combination of v1 to vp. We already have this. Now, given v1 and v2 in the vector space, let H be the set that is spanned by v1 and v2, so that H is a subspace V. Now, this is actually a proof show that it is a subspace. So we need to prove 3 things. The first one is the 0 vector in H. So can we do that? So, by the way, the span of v1, v2, if we're going to write that out, H will be the set of all the linear combination of v1 and v2. So we could say C times v1, C1 v1 plus C2 v2. Yeah, the set of all of those linear combination, where C are C1, C2 are real numbers, so I just say set of real number. Right. Now, is 0 belong to this set? And that's easy, right? So we say C1, V1, C2, V2. If we choose C1 and C2 to be 0, then we have 0. Right? So if we choose C1 and C2 to be 0, we have a vector 0, and the vector 0 belongs to this set H. So we have the 0 vector inside the set H, so that's good. The next is that close under addition. Right, so we're going to prove like this. Let's say we have x1 of course can be written as C1 V1 C2 V2, and now let x2, let's say D1 V1 D2 V2. Both of them, of course, because it's written as a linear combination of V1 and V2, belong to H. That does belong to H. This belong to H. By definition, a a set spanned by v1 and v2. Now then we just written what is x1 plus x2. Well, we just combine them, right? When we add them, let's just write c1 v1 c2 v2 plus d1 v1 d2 v2. We can factor out v1 v2, so we have c1 plus d1 v1 and c2 plus d2 v2. Now since we write like this, we have a constant times v1 plus a constant times v2. Because we write like this to satisfy the linear combination of v1 and v2, therefore this belongs to the set H, because it is a linear combination of v1 and v2. So yes. And the next one is that closed under scalar multiplication? Right, so let x be c1 v1 plus c2 v2. So that is an element of H, a linear combination of v1 and v2. Then when we multiply c by x, let's multiply a into x, because we have the c already. When we multiply a into it, we're going to have a c1 x1 plus a c2 x2. Once again, we have a constant times x1 plus a constant times x2. This of course also belongs to the H. So as long as we see any element in the set H multiplied by a constant, we also have an element in the set H. So that is closed under scalar multiplication. If we have an element in the set, when we apply some operation, if it is still in the set, that means it is closed under that operation. Since they satisfy all three properties, we say H is a subspace of V. Yeah. So most of the problem in this section, the calculation is fairly simple. However, the concept is a little more difficult. But for the subspace, we need to prove those three properties. It has no content 0. It is closed under addition and closed under scalar multiplication. Right here. If we have the vectors from V1 to Vp in the vector space V, the span of V1 to Vp is a subspace of V. We call that a subspace span or generated by the vectors, the set of the vectors. Right. Now, more sample. Let H be the set of all vectors of the form A minus 3b, b minus a, and a, b. So 4 components, where a and b are arbitrary scalars. So I can write like that. Show that H is a subspace of R4. So first of all, we have to write 3 criteria that we need to show. First is the 0 vector in H. Right. Now we write a vector that is an element of H, written in this form. Now, can we make this equal to 0? And the answer is yes. If we choose A and B to be 0, then that is 0 and that is 0, right? So if we let A equal to b equal to 0, then x equal to 0, a 0 vector, right? If a and b are 0, all of those are 0. So the 0 vector is in the set H. Check. Next, is it closed under addition? Right. So in that case, we're going to get two random elements in H, combine them, add them to see if it is still in H. So we say let x1, the first component, just say a1, 3b1, b1 minus a1, a1, and b1. So when we write like that, this is an element in H simply because it has this form. By this form, I mean the third component, the fourth component. When we subtract them, we have the second component, and certain combination give us the first component. Let x2 be a2, 3b2, b2 minus a2, a2, and b2. Let this be in H, an element in H. Now, how about x1 plus x2? We just combine them, right? It's easy. We combine them all across. So a1 minus 3b1 plus a2 minus 3b2, b1 minus a1 plus b2 minus a2, a1 plus a2, b1 plus b2. Right, I just add them. Now, let's rewrite this. a1 plus a2 minus 3 a b1 plus b2 b1 plus b2 to the bracket minus a1 plus a2, then a1 plus a2, b1 plus b2. So what we see here is this belong to H. Well, how do we know that? Well, if it have these properties. Right, these properties meaning that, look at the second component. It is the fourth component minus the third. Now we look at this. It is the fourth minus the third. And then look at the first one. The third component minus 3 times the fourth component. So the third component minus 3 times the fourth component. So yes, it have that form. So definitely it belong to H. So yes. And now go to, is that closed under scalar multiplication? I said the math, the computation is simple, but the concept is a little new compared to the course that you've been studying, I assume. So first, we're going to let x be an element of H, meaning that we take this form. Then if we multiply a number into it, what do we have? course we just multiply C into it, and we have CA minus 3 CB minus CA CB. Now compare this with the original properties the same way. The fourth component minus the third component, the fourth component minus the third, so the fourth minus the third. And then this the first component minus 3 times the third, the first component, the third component minus 3 times the fourth component. So it has the properties of, it have the same form as the vector in H. So this belongs to H. So it is closed under scalar multiplication. All of that just to show that it is a subspace of R4, right? So it has all of those 3 axioms, 3 properties, 3 criteria, so that H is a subspace of R4. Right. Now, for this one, show that the set H of all the points in this form is not a vector space. Well, this is the vector space, so we have to prove all 10 of them. However, when we say that it is not, we only need one counterexample. And usually the first thing that we look for is that it be equal to 0. So we say let the point x be 3s and 2 plus 5s. Let that be a 0 vector. Can it be a 0 vector? Well, in this case we have 3s equal to 0, and then 2 plus 5s is equal to 0. This is equivalent to saying x equal to 0 and s equal to negative 2/5. It cannot happen because s is just one value. It cannot take 2 different values at the same time. So that would be the 0 cannot take this form. This form cannot be equal to a 0 vector, right? For this to be 0, s have to be simultaneously equal to 0 and equal to negative 2/5. It cannot. In here, yeah, it can be equal to a 0 vector if we choose the values to be all 0. Now if we choose s to be 0, this is still not a 0 vector. So since 0 vector is not inside H, so it is not a vector space, because a vector space has to have 0 in it. If we want to prove something a vector space, we have to prove 10 axioms, all 10 of this. But if we want to show something is not a vector space, we only need one counterexample, or one axiom that is not true, then it all fails. Now, for the following graphs of function on xy coordinate system, let H be the collection of all the points on the graph. Is H a subspace of R2 using the normal addition and scalar multiplication? So in this case, we can say all the points on this graph as x, and then x squared minus 1. So H will be the set of all of those vectors in this form, the points in this form, anyway, where x could be any real number. Right. So is H a subspace of R2? In order to be a subspace, there are 3 criteria, right? So first is 0 in H, and obviously 0 is going to be the point 0, 0 here, and that is not in H, right? Because the point is not on the graph. The point 0, 0 is not on the graph. So the answer is no. 0, 0 is not in H. So this fails. So we say H is not the subspace of R2. Simple as that. Next, we have negative 3, the function equal to negative 3x. So the set in this case is the set of all the points in this form, x and negative 3x, where x is all real numbers. Right. Now we will prove. First of all, is the zero vector in H. Well, we see the graph, it goes to the point 0, 0, right? So the answer is yes. Go to the next. Is that close under addition? So we will pick a point in the graph, pick another point on the graph, combine, add and add them to see if we still have the point on the graph. So we see, we write, let's say we have the point x1 and negative 3x1. That definitely will be on the graph because it has this form. The first component and negative 3 times the first component. So this is in H, right? Let's say this is x1 and then x2 will be x2 minus 3x2, and that, because of written in that form, is also in H. Now we will combine them. x1 plus x2 so I have x1 plus x2 and then negative 3x1 minus 3x2. Yeah, just combine them. And then we can factor x1 plus x2 minus 3 x1 plus x2. Sorry, bracket and then parentheses. Yeah. Since it only so have in this form, as you see, the first component and negative 3 times the first component, so this is definitely in H. So that is closed under addition. So if you pick a point like x1 negative 3x1 and then x2 negative 3x2, and then when we add them, we will have, it will be a point somewhere in here. Now is that closed under scalar multiplication? So I picked the point x in H, so it has to be the form first component negative 3 times first component. This is certainly in H because that has the form of an element in H. Now if I multiply by C, multiplied in, we have cx1 minus 3cx1. As you see, we have the first component and negative 3 times the first component. This certainly is the same form as an element in H. So C times X is in H. So that's why this is closed under scalar multiplication. So since they satisfy all three actions or three criteria, we say the set of all the points here is a subspace of R2. So H is of subspace. This H is a subspace of R2. Right. Next, we have this example. Once again, if we're going to write this, it will be the form of the set on the point in this form. Our x is any real number. Right. To show that it is a subspace, we need all three criteria. Right. And so we see that in this graph, yes, it actually is. And then next is that close under addition. Right. Once again, we pick the point in H. We satisfy. We'll have this form. So I will say x1 will be just x1 and absolute values of x1. This is in H. Now just pick another point in H. Of course, we'll take the form of x2 and absolute values of x2 in H. And then we add them. Now, is this belong to the set H? Right. It depends. Now, if we can write if it is in this form, then definitely will be in set H, right? Because this is the first component and absolute values of the first component. Now this is slightly different. My question is absolute value of x plus absolute values of x1 plus absolute values of x2 is equal to x1 plus x2? And the answer to that is no. Think about this. Let's pick a point. Very simple. 2 and 2 belong to the set H. And pick another point. If you add them, what do we have? -5, -1, and that is not in H. The point 5 and -1 is here. It is not belong to the graph. Right? So why do I come up with this counter example? Well, look at this. If x1 and x2 are all positive, then this will be true. It will be in H. But if we choose one point on this side, one point on the other side, when we add them, this and this will not be the same. So this one is not closed under addition, so it is not a subspace. because it is not closed under addition. So if we pick 2 points on the same side, it will be closed. But if we pick 1 point on this side, 1 point on that side, when we add them, it's not in the set H. So that's why this is not closed under addition, so H is not a subspace. So in order to be a subspace, it has to satisfy all 3 criteria. Right. Here I will be just go over this rather quickly. Let P star 2 is the set of all the second degree, so it has to be second degree. Is P2 a subspace of the polynomial? I could see how about 0? Is that in the set here? What is a 0 vector in a polynomial? Now think about this. A polynomial will be in the form of, let's see, the set of P will be, I just write reverse, A naught plus A1x, A2x squared, A3x cubed, and so on. A 0 vector will have all the A1, A2, A3, all of that have to be equal to 0, right? So that is equivalent to 0 vector, but it is for polynomial. So in polynomial, zero vector is equal to 0 plus 0x plus 0x squared, and so on. However, is this belong to the set of second degree polynomial? And the answer is no, because this 1 degree is equal to 0, right? So since 0 has degree of 0, it is not in the set of second degree polynomial. Let us P2 star is not. So P2 star is not a subspace. Of a polynomial, because it doesn't have a 0 vector, so it's not a subspace. Right, so it fails. Next, is the set of all these points in this form a subspace of R3? Well, to check, is the 0 vector in the set, this on this set H? Is 0 in the set H? Well, so we're just going to write, if it is an element in H, it has to take the form of that. Let's say if it is equal to 0 vector, that means A have to be equal to 0, A squared have to be equal to 0. So those two are okay, but 3A plus 2 equal to 0. So that implies A have to be equal to 0, and that A equal to 0 is good. So A cannot simultaneously equal to 0 and negative 2/3. So this cannot be equal to 0 vector. So we say 0 is not in H. So it's not a subspace. So, as I mentioned before, the exercise in this chapter, the math, the computation is simple, but we will have to get the idea. Mostly to prove a subspace, we will have to show that 0 is in the subspace and it is closed under addition and scalar multiplication. Meaning if we have an element in the set, another element in the set, when we add them, is that still in the set? And to prove that an element in the set, it has to satisfy the some characteristic of an element in that set. And so in this case 0 is not in the set, so it cannot. Right, here's another example. Let V be a set of 2 by 2 matrices of the form A, B, C, A. So the characteristic of this element of the set is that in this case it is the 2 by 2 matrix, but the diagonal entries are equal. So that is the characteristic of an element in the set. Now, is V closed under matrix addition and scalar multiplication? So we're just going to check. Now, if we have A1, B1, C1, and A1, is that belong to the set? And the answer is yes, because the diagonal entry are equal. So it satisfies the properties of the characteristic. It has the characteristic of an element in the set, so it is in the set. Now if I add another element in the set, this element is also in the set because it has the characteristic of the diagonal entries are equal. So this is in the set, this is in the set. When we add them, what do we have? A1 plus A2, B1 plus B2, C1 plus C2, and A1 plus A2. What we see here is that the diagonal entry once again are equal. If it equal, that means it belongs to the set. So this belongs to V, this belongs to V, the addition also belongs to V. So that's why it is closed under addition. Right, now scalar multiplication. For scalar multiplication, we pick a point that has this form. So maybe A1, B1, C1, A1. Once again, this is in V because it has the characteristic of an element in V. Diagonals entry are equal. Now if we multiply by a constant, let's say K to it. Now, is this also in V? How do we know that? Well, if it is an element in V, the diagonal entries have to be equal, and they're equal. So we say this is in V. So this one close under multiplication, scalar multiplication. Yeah. So original, this element is in the set V multiplied by a constant. The result is also in V. So that's why it is closed under multiplication. Right. Now, not only I mentioned that when we talk about vector space, it doesn't have to be a vector. It could be anything, polynomial, matrix, or all other things. Not only that, the operation we can also define to be something that is unconventional. For example, we define addition. This is just the regular addition of vectors. However, when we define the scalar multiplication, it is only multiplied by the first one. And this say that under these operations, action number 8 fails. This is number 8. So let's see why is that the case. So number 8, in this case I will write out, we have x1, sorry. Right. So this is the case. Now we have C plus D equal to Cx and then you say, why do I change the addition to that addition? Well, that is the case, right? So when we combine two vectors together, we're going to use that operation, but this is just the addition of two numbers, so that's why just the regular plus here, just addition of two numbers. However, this is the addition of two vectors, so it has to be in that form. And let's be clear, it is not even that. It should be this. We have C plus D. That is just addition of two numbers, so nothing special here. However, if we have a number times a vector, we have to use this operation because that's the way we define it. So we have to have C multiplied by X and then plus D multiplied by X. And the question is, we don't know if this axiom is true or not. Once again, we have to use the scalar multiplication when we have a number and a vector, and when we have two vectors and we want to add them, this have to be this operation. Right, now just do the left hand side and the right hand side and shows that they are not equal. That is the goal here. Right, left hand side. The left hand side is C plus D and then multiply to the vector X and let X be XYZ. Right, so we have C plus D multiply the vector XYZ. In this rule, we only multiply to the first component, not the whole thing. So I multiply to the first, the second and third, just stay as is. So that is what we have on the left hand side, using the operation that they give us. Now the right hand side. The right hand side is going to be C multiplied by the vector X plus D multiplied by the vector X. Of course, multiply first, add and subtract later. So C times X. When we do the scalar multiplication in this definition, it is only multiplied by the first. Addition. And then multiply this D into it, we have dx, dx, y and z. This special multiplication only multiply to the first component. Right. Now we add them. See, when we add them, this is just a normal addition. So we just have cx plus dx and then y plus y, c plus c. So what do we see here? What we see here is that they are not the same. So the left hand side is not equal to the right hand side. So that's why this axiom number A fails. Right. So To make things more abstract, more general, we say that it doesn't have to be a vector addition in the normal way. In this case, actually, it is in the normal way. We can define any form of addition and any form of scalar multiplication. If we define using this scalar multiplication, the axiom number A fails. Yeah. So that is the end of section 4.1. Thank you for watching. See you in another video in linear algebra.